last class, we went through on how to derive the material indices for a simple case of an axially loaded bar. Okay. If you recall, how did we start? We wanted to design a lightweight, stiff, axially loaded bar of a particular given length. So this is a fixed length according to the application. And what other dimensions? I think the length is one of the fixed dimensions. So what is the objective? We wanted to minimize the mass because it is lightweight, and we want to have a stiff bar. Maybe we were also given what should be the stiffness in the case. So assuming stiffness we derived. Okay, so maybe it was given should be greater than or equal to this value. Then based upon this value, we have to figure out what is the material index. So how did we start? Objective function, we want to minimize the mass. We identify what are the free variables. L is not a free variable. The area of cross section is a free variable, and the shape of the cross section is also free variable. Okay. Besides that, the material is also free variable. So we had to include material choice because the density is a free variable. Once we identify that, we want to minimize mass, and mass we wrote it in the form density times volume, density times area times length. L is fixed, we cannot do anything. Rho we can change, A we can change. Now the idea is to replace the free variable, geometric variables, usually in some other form. So we have the stiffness formula. We write the equation of stiffness as force over the elongation, and we get, this is from your typical spring equation, that should be equal to greater than or equal to, we can write S star. Okay, so if that is the case, keeping this as equal sign, we want to get for the stiffness a formula. Okay, so how do we get it? From Hooke's law, we rewrite the equation and then express it in the form F is equal to K times delta. F is equal to EA times L or times delta, and we get stiffness is equal to this EA over L, which should be S star, and then we replace A in terms of other properties. So when we do that and substitute inside the mass, this is the form we get. Now usually what we do is we group the terms together, stiffness on one side and the other material properties on one side, geometric properties on grouped together in one term. When you write it in this form, we get the material properties. When they are grouped together, we get what is the material index in this particular case. So what is the material index we get? This is the material index, but we want to minimize the mass, so which means I have to minimize this guy. The greater the density, the greater the mass. So I have to ensure that my density is smallest to minimize mass, and E is highest to minimize mass as well. So which means I can take the inverse of this guy and then maximize this quantity called material index, which is given by E over rho, and that will automatically minimize mass. Okay, so I'll just show you. We'll go through one of the softwares. Unfortunately, it's not available for free. I'm just going to demonstrate how this material index can be used in the software to figure out what are the appropriate materials for this application. Okay, so CES EDU pack is one of the softwares. You have 3 levels here. Level 1 will have materials which are, we will not have much choice of materials in level 1. Level 2 you have much more choice, and level 3 even more choice. Okay, so let's try level 2 here. Now how do I select the materials? On the top here you will see chart select. If I click on it, this particular toolbars they open, and then I can click on chart. Once I click on chart, there is the choice to have there is the choice to assign variables to the x-axis and y-axis. There are various types of variables. Here on the x-axis, based on the material index, what we have seen here, I'm going to use the density as the variable in x-axis. So based on that, first I need to choose the category here. I go for general properties because these are physical properties and not specifically mechanical properties or other properties. And under that general properties, you can see price, etc. Density, you can choose density, leave it in logarithmic scale. Let's go to y-axis, and in the y-axis I want to choose Young's modulus, which is a mechanical property. And if you go down, you can see compression, bulk modulus, fracture, mechanical coefficient, Poisson's, shear, Young's modulus at the last. So you can plot this graph, leave it in the logarithmic scale, and press OK. So this is the graph I get. So in your exams, I will create these graphs and provide you directly. All you need to do is use these graphs. But in the software, you can see here, if I move my cursor in each bubble, it will give you what kind of materials these are. So these are foams, and then we have flexible polymer foam. All these are foams. All these bubbles are foams. Then we have cork, rigid polymer foams, again metal foams. You can see various other types of materials which are listed here. As I go up, you can see slowly we are getting composites, and let's see here, CRFP, and then we are getting some metals, small bubbles here. They give you the metals and ceramics, titanium alloys. Okay, so these are the various types of materials. Now how do I use this? How do I use this material index? I have to draw a line, representing this material index, or the ratio of the values, E over rho. Okay, let's see here. Go back to the slide for 1 second, and you can see here E over rho lines are represented parallelly here. So in the same way, we should be able to draw these lines. Let's see here. Okay, so these are the index lines, and you can see here the slope here. Slope here is usually represented by the beta value here. So if beta is different, I can provide 1/2 value here for the slope. If beta equal to 1, then I can provide it is equal to 1. So we want to maximize the index, so I leave it as the objective function, maximizing the index. If you want to minimize, you can choose to minimize depending upon what kind of material index you get. Okay, so let's put OK, and we can draw the slopes here. So let's try drawing the slopes, and where corresponding to, and you can, wherever you click, you can see here the slope appears. Again, Okay, let's say I want to start from this point. It gives you the slope. Okay, so once I draw the slope, you can see this, all these materials here, they go on a grayscale. That means they are removed here. So results are 87 out of 100. So let me see if I draw again one more slope right at this point. Observe here you have results 87 out of 100, and if I click here, immediately the materials are removed from the list. By drawing this line, only materials above this line are considered. Okay, so in the same way, you can manually do the same thing. Well, once I provide a chart like this, you will be able to draw some lines. And since you want to maximize, that means you want to go in this direction above and specify only materials above the line to be selected. Now, besides this, we can also draw certain lines horizontally here. Suppose if you want to select only materials above 100, then you can draw another line here and only select those materials which are above here. Okay, so let's see if I want to select only of materials of certain density and certain Young's modulus values. So I will be able to draw a box here, box selection, and you can see only materials in this area will be displayed. So this is how I can use my material index by choosing only certain type of materials to be used. Okay, so simple example, you will do this manually. Okay, similarly we can create other charts as well. So let's see here.
Doctor,
Yeah,
how I know where I drew the slope?
okay, so the values, okay, you will have to calculate. For example, here this is on a log plot. Okay, so log of Young's modulus value is 0.01. Okay, and the particular density value can be uh, obtained from the x-axis. So let's pick up any point. For example, if I pick up this particular point here I do not know. I think the log value should be 1 here, right? 1, 10, 100, 1000, like, etc. So the log of Young's modulus value here is 0.01, and the log of density value is 1. We should be able to calculate the value here. In the same way, if I go to this point, let's suppose I know what is the log of this value, Young's modulus value, and the log of density value here. Based upon these two values, I should be able to figure out what is the slope. Okay, so here in this particular example, uh, I do not know exactly what is the value. Okay, so how do I figure out? In such a case, here I have to draw more lines. You can see more divisions here. Okay, so for each of these divisions, if I know the values, corresponding values of the density, then I can draw vertical lines and find the intersection points and then try to figure out what is the slope. In general, how would I do this? Okay, usually I will try to draw these lines. Okay, or when I draw these lines, I should ensure that they pass through one of these intersection points. If I'm not able to find the intersection points, what I will do is I will find the approximate values here. Okay, so let's see here. In this case, I try to draw the line right through this point. Let us try here. What is the slope? So first value, okay, go back to the notepad. Okay. Let me note down here. This is the lecture 7. So one of the points, log of E is 0.01 and log of density is 1. Go back here and try to figure out any other point that is possible for this particular line. It is intersecting the line here right at this point. And let's say this is approximately about 40% from here to here. Since these values are difficult to obtain, maybe we don't have any intersection point right at this scale. Okay. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8. 7, 5, 6, 8, 9, 10. So equal divisions. So 1, 2, 3. So let's consider this point here. Okay, so log of E is 0.1. We can write here the second point. So and then here we have 3 divisions, 1, 2, 3. Approximately we can take this to be 3 divisions. Okay. The log scale, we have 3 divisions. We need to figure out what is the value. Okay. So let's assume, okay, so this is 100 here. 10th division is 100. The first is 10. And let's assume that is equally divided. Okay, so 1, 2, 3. This is the third division. So we have 10, 100 value and 10. And then see, we have 10 divisions. So multiply this. First, let's find this value. We have 90 by 10, so approximately 9. In these values 9, let's say we have, no, I think this is wrong. We should get 10 here. So let's count here. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so each one is at 10, about 10 divisions here. So we can take this value approximately here as 30. Log of rho here is equal to 30. Okay, so each division is about 10, not 9 here. So from here I would just get rid of this. So look at the graph here. Let's take each division about 10 here. Between 10 and 100, you will assume each division is 10. So you will have 20, 30, 40, right? So 10, 20, 30, 40. So this division corresponds to a value of 40, not 30. Let's write it as 40. Okay. Now, based upon these values, these two, the first point and the second point, you should be able to calculate what is the slope. So let's see here. This is in the log of the values, remember. So if you want the E over rho value, take the second point here, since this is the log of the value, I will assume this is base 10. Okay, all these are base 10 values. So 10 power 0.1 minus 10 power 0.01 divided by the corresponding density values. Let's see if this will come out right in the kg per meter cube values. This is in kg, this is in gigapascal. Okay. Remember, in the numerator we will have it in gigapascals. So we multiply by 10 power 9 here, and then here we write it as 10 power. That doesn't come out right as well. Kg per meter cube. Now, yes, you will get maybe very high values here. Minus 10.
Doctor,
Yeah.
here's the coordinate in the corner. We can give you from the program.
Where is the coordinate in the corner?
Near the Windows logo, in the bottom corner.
Here in this chart, you mean?
Yes, keep the mouse in the chart and look at
Okay.
the bottom corner
Okay.
near the
Yeah,
Windows.
right. So we do get x is 3.89. Okay, let's see here. No, this coordinate is doesn't work. Okay, why I tell you, because the values are completely different. Look at these coordinates. It is just giving you the pixel coordinates. When I move it in here, let's see, this is 10, x is 10, 10.7. Okay, so this is coming out right. Let's go here. Okay, so it does give you the coordinate. X is 10 and y is 5.95. Let's go here, 36.3, so around 40. So this intersection point approximately comes out to be 40, and this is 0.1. Yes, so it's the same value we are getting. Okay, so if you look between these points, we are getting about the same value. About 10 here, and the y coordinate is 0.0 something. Okay. Okay, so between these 2 points, based upon this ratios, by looking at the coordinates. Specifically, you will not be able to have access to this software. What I will give you is the chart itself, but using the chart by manually drawing these points, you should be able to find out what are the values. This is why I provide you the approximate value. Now I show you how to extract the approximate values here. So right here, you know, if you go to this point, approximately we can get the values as 40, 10, 20, 30, 40. So if you are anywhere in between this point, for example, you see the divisions here. And based upon these divisions, we take the values here. So between these 2 points, you will take the values 100, 200, 300, 400, 500, 600, 700, 800, 900, and 1000. In the same way, between 1000 and 10,000, the divisions represent 1000, 2000, 3000, 4000, like that up till 10,000. So this is on logarithmic scale on the x-axis. On the y-axis also, it is on logarithmic scale. So between these 2 points, for example, you will have the value 0.01, 0.02, 0.03 up till 0.1. Between these two, it will become 0.1, 0.2, 0.3 all the way to 1. Between 1 and 10, the divisions represent 1, 2, 3, 4 up till 10. Between 10 and 100, the divisions represent 20, 30, etc. Okay. So when you want to find the slope of a particular line, based upon these divisions, approximately you can get what is the value of the slope. Okay. Now, how will you know whether it is increasing or decreasing? When I'm moving this side, the ratio is increasing. When I'm moving down, the ratio is decreasing. It's very easy. You don't need, there is no need to calculate and see that. You can see here when I'm down here, the E value is pretty less. Okay, and the rho value is pretty high. Therefore, E over rho is very, very small in this corner. And if I go up here in this corner, perpendicular to this guy, I can clearly see my E values are higher and my rho is decreasing. So I clearly know my E over rho ratio should increase in this direction. Okay. Okay, so it is not necessary to write down the values and figure out what is the E over rho ratio. Okay, but when I ask you the problems, when I ask you to solve for the problems, I will not ask you to figure out what are the values of E over rho. I will ask you to find the general method where I want to maximize my E over rho ratio. So where I can maximize, when I draw the lines and I move in this direction up, it will automatically get maximized. I do not ask you to maximize to a particular value, but generally in this direction, it will get maximized. You can also select based upon E values. Maybe I will tell you the E value should be greater than certain gigapascals. Then based upon the value, you can choose greater than that value means you have this value here. Okay, specifically those values. Okay, so I let me be sure, because these values may be also doubtful. What I think here is possibly, although it is plotted on the logarithmic scale, although these guys are plotted on the logarithmic scale, I still think these are just absolute values of density and Young's modulus. Okay, looks like this should not be the case. I assume these are log of the values. However, I think the displayed values itself, although it is plotted on the logarithmic scale, the displayed values itself is not on the logarithmic scale. Okay, so I think those are absolute values. Sorry for this. I'm going to delete this guy. Okay, so let's okay. So although the displayed values, I think by looking at these values, it looks like these values are in the absolute values of density rather than being the log of the values. Okay, the scale is logarithmic, but the displayed values are not as such. So, so what can we write here? Actually, to calculate the slope, here, we have the density 1 value. Let's assume this is 0.1 here. Okay, so rho 1 value is 1 kilogram per meter cube, right at that point, right at this point. Okay, and then when we go here, it is 10 kilogram per meter cube. Okay, so disregard what I told before. The displayed values here looks like these are absolute values of density, because that makes sense. Okay, and here let us see here 0.01 gigapascal. Okay, so this looks like E1 is 0.01 into 10 power 9 pascals. And E2 value, let's go here, approximately, right, 0.0281 gigapascal. So this appears to be right, and this should be the right one. So the values displayed here, these are the correct values of E in gigapascals. Okay, so these are in gigapascal. However, these values are scaled in the logarithmic scale. Okay, while here also these are density values. Now you will be able to easily calculate the slope. Slope of any line is E2 minus E1 over rho 2 minus rho 1. Now it makes sense. Yeah, so let's see here. Times 10 power 9 divided by 10 minus 1. Okay, so this is how you can calculate the slope approximately. Even if you do not know what the values are here, I have showed you in the logarithmic scale. It will be 20, 30, etc. and you can approximately get what is the slope if you are required to get the slope. On the left hand side, you can see many different materials. For example, within this box, if you are interested only in metals, you can go through. If you have access, maybe later at a later stage, if you get the access, you can see here data sheet. Right click on it, and low alloy steels, it will display all the material properties. Okay. By the way, ANSYS, I am not sure if it is available in University of Bahrain computer labs. If it is available, the paid version may have this particular software embedded in it. Okay, specifically this material selection software could be found in the ANSYS software. And it is not available in the student version. However, a paid version may have this particular software present in it. Okay. Okay, so let's move back to the slide. We'll go back to the slide here, and we'll go through some other examples of deriving the material index. Okay, so again here, explanation given. P stands for any performance function. In our case, the performance function, depending upon the statement, could be mass or some other function. So when you have mass, we split it into three functions. One is the functional form, like your stiffness value, then function of geometric parameters, then multiplied by function of material indices. So this is how we will be splitting it, and then we will be taking the third part, okay, consisting of material properties as the material efficiency coefficient or material index. Okay, so this will be material index as well. So let's see if we have more examples. Okay, so here we have an example of a beam, deflection of a beam, and we want to figure out what is the material index for a beam. So let's go here to the notepad and try to derive. I want you guys to participate here and then figure out what is the material index of a beam. So let's go back to the question here. What do we want? Light, stiff, end-loaded cantilever beam with a circular cross section. Okay. So what is the objective here in this case? Can one of you tell me? Stiff, end-loaded cantilever.
Minimum mass.
Minimum mass. Okay. End-loaded cantilever beam. So first objective, we have to write clearly what is the objective. Mass is equal to, let's write minimize, since it is light, mass. So I will write the expression as well. Rho into, since this is a beam with a circular cross section, whatever is the area of cross section, I'm going to represent it as A times some length. Okay. Then we identify fixed variables. So before we do that, let's just draw the diagram of a cantilever beam. Okay. This is the cantilever beam, circular cross section, and let's assume L is specified. Usually in the design, the length L of a cantilever beam is specified there. We cannot do much about it. And now we identify fixed variables. What are the fixed variables here?
The shape of the beam,
Shape.
circular,
Right,
and
shape
L.
of cross section. And then length, right? Length is fixed. So no choice here. Let's identify the free variables. What are the free variables? What we can change here?
The material.
Material. That means rho. So in the bracket, I can write density. Then the shape of cross section is fixed. However, the size, what about the size? No, right? So the radius or the area of cross section, A, is not fixed. So a is a free variable. Okay, so we have identified objective everything. Now we write it. What else before that? Here, light stiff. So we never talked about stiffness. What about stiffness? Is it free variable or fixed variable?
Fixed.
Let's assume it is no. We want a stiff beam. That means we want a high value of stiffness. Okay, so in that case, let's assume stiffness is supposed to be minimum a certain value, so greater than or equal to, let's get some S star. Okay, now we go here, we rewrite rho times A times L. Okay, we know rho and A are free variables, L is fixed. Now we need an expression for cantilever beam. So I'm going to use a ready-made expression here. Okay, so the deflection has to be minimum, right, for a stiff beam. So we need an expression for deflection, and this is the, once you derive the expression, this is the expression you are going to get. So usually after writing the equation for mass, we will require deflection equations or some other equation. So what is the equation we have? End loaded. Since it is end loaded, that means we have a load F at the end of the cantilever beam and length FL cube over 3EI. So that is the formula we are going to use. Okay. So if you look at this formula, we need an expression for I. Since it is a circular cross section, what is I? Anybody? What is the moment of inertia of a circular cross section? 64 d power 4. So this is the formula. Now I want to replace A here. This guy has to be replaced. How do I replace? I need to get an expression for A here. Okay, so that is the main aim. So what I'm going to do is rewrite here. I know S star stiffness must be equal to force over delta. Now if I rewrite here F over delta, the above equation here, F over delta, I will get this is equal to 3 EI over L cube. But I is equal to something, so now I need to come up with an expression for I. What is A? Area of cross section A is nothing but pi d square, pi over 4 d square. Sorry. Okay. So we need to rewrite the expression here somehow. I has to be expressed in terms of area A. So let's try to do this. So let me put pi over 4 d square whole square. What will be the result? I'm going to get pi square over 16 d power 4. So I have to factor that out of this guy. Okay. So I have here in the denominator 16. So 1 over 4 is already outside. So I can just write 1 over 4. So I get in the denominator 64. In the numerator I get pi square, but there is only pi here. So 1 over 4 pi on the denominator. So now I have pi over 64 and d power 4. So clearly I can be written as a square over 4 pi. Okay, so now I substitute and I get 3 e a square 4 pi L cube. Now I have expression for A. A can be substituted. A square root of something. Take all the terms to the other side, 4 pi L cube S star over 3e 1 over 2. Now take this expression and substitute inside the mass expression here. M is equal to rho times A. A is this guy. Put the square root. Times L. Now we can group the terms together here. M. Okay. Take the functional properties like S here. Square root of S. Put it commonly outside. Geometric parameters. You can put it outside. Maybe group. Since we have 4 pi, I'm going to group it with the functional parameters. Divided by 3. Okay. Group the geometric parameters. We have L outside. Yes, we have taken 4 pi. Okay, so L cube and then multiplied by L power 3 over 2. So this is the functional parameter. And finally we have rho over square root of E. So our material index is right here.
Doctor, time's finished.
Yeah. Pardon? I will just finish this. So this is our material index. I'm going to write the material index as square root of E over rho. Okay. So for our beam, this becomes our material index. And if you go back to the, let's see here, how do I go back to the chart? Here. Okay. So I can see the tabs here. I can click on the chart here. And let's say I delete some of these guys. Instead of drawing this particular line, I can draw now my slope here as 1 over 2. Okay, so rather I should put 0.5 because it won't recognize 1 over 2. And I want to maximize this quantity as well. Okay, so I will be able to draw these slopes. You can see here 0.5, maybe from this point, and I can draw lines square root of E over rho. Okay, so by drawing these lines I will be able to figure out the same thing. So we have to maximize this index. Okay, so we are done for the class today. Next class we will see more examples and you will definitely get a problem, at least 15 marks worth from material index selection, and you'll have to give a reasoning. Okay, so let's see if we have more examples on these slides. We go down. Okay, so more examples on the slide based upon strength. Okay, strength parameters, and we are going to see these examples. Okay, any doubt up till now? If you do not have any doubt, I'm going to stop right here and we will continue from next class on Tuesday. Okay, see you guys.